Yeah. Okay. Can you move this auto?
Yeah, because the speed is not up. Okay.
Yes. Yes. Thank you for the time. I mean, this also is really very good for me to always to keep practicing, to always increase the knowledge, so that, I mean, because before giving any presentation, we have to, I mean, we have to keep reading so many things. So first of all, this my work about the geothermal exploration in Saudi Arabia. In Al-It is the western part of Saudi Arabia. No. Okay, it's not working. Basically, I will talk about the introduction, and then also about the basic theory a little bit, and then data acquisition, and then also data processing, and then different type of inversion, 2D and also 3D. And then the last thing is just to acknowledge some people to, who deal with this job. Okay, first, I will explain, this about the geothermal in Saudi Arabia. What happened? Okay. Sorry. I can classify into, like, let's say, two periods. So first and the second period, because if I see, the year, for example, there is like a long gap between the first period and the second period. In the first period, like we start, 1974, 1982, we already, preliminary studies about the geothermal in Saudi Arabia. They carry out some analysis on the hot spring sample from the hot spring, and also did some limited geophysical method, and also some analysis on the volcanic field. But after like 1994, there's like a gap, until like 2013, then there is, another studies about geothermal, because, somebody, there is also paper to, discuss about this gap, what happened. They suggest that it's, political issue, because Saudi Arabia is very rich in oil and gas, where they will develop like geothermal. This is like the main reason. But since like 2010, they introduced new vision. They call it Vision 2030. Vision 2030. They realize that they have to develop the economy. They have to increase the share of renewable energy and so on. And then after that, this starting, that's why, after like after 2010, it's many studies like 2013 from Hussein, and 14, 15, and so on, about the geothermal analysis. They again, major like chemical analysis. They also do some geophysical survey, and then in this period, they already know, like, become more focused in specific area and so on. Sorry. And then from this so many studies, there are some conclusion that yes, the Saudi Arabia is can be classified as a geothermal rich energy, because they have a couple of places, but mainly in the western part, from the north to the south. And then this the The right polygonal is the from the volcanic, and then the triangle is hot spring. And then another conclusion saying that the most promised geothermal system is in Awit. Awit is here because they are like 4 hot spring. In this, I mean, 4 hot spring, they suggest that Ein Hara hot spring. There is the name they call it Ein Hara. Where is it? Yes, Ein Hara. It's like the most important field in Saudi, I mean, in Saudi Arabia, in geothermal field, because what happened is the temperature is like the highest temperature in the hot spring. And then also, I mean, if you compare with other geothermal field, it's really, I mean, like a big difference. That's why nowadays, some studies is focused on this Ein hot spring or in Awit area. However, they I mean, you know, did some experiments, some survey, but still we have to you know, I say, I mean, because the result what they produce is not really reliable. What happened is they did also like seismic resistivity, I mean ERT, this like for shallow I mean studies. In fact, in geothermal, we have to reach like I mean deeper part, I mean 7 or 10 kilometers. That's why I mean we have to, I mean, still need more comprehensive work on this geothermal field. We already visit this area and we did also some measurement. This is the Ein Al-Hara, I mean, hot spring. They already did some refreshment and also let's say some bath. We can go, and then this, I mean, steam is always going on. I mean, the water here is very hot, so we can do like a steam bath here. It's very nice. I mean, place and they already did, but still we have to, I mean, analyze the reservoir in subsurface. Another introduction I want to show is about the geological setting. So this is the Ain Al hot spring, and then this is the Ain Awid. It's located below Mecca or Jeddah. So next to Jeddah. And then in this part, in this geological setting, basically we have like a sand area. So this part is we call it like the path or the fairway contains basically I mean sand, sand, and then this another part like a different you know, different type of rocks. So in this study we I mean I have at least 3 objectives. First is to perform MT and TEM, because in geothermal like the main method to do to analyze geothermal reservoir is using MT, because it can go deeper, and also I mean there is like a direct correlation between the temperature liquid to I mean to have like a conductive anomaly in geothermal system. And then another thing is we can, you know, analyze to mapping, let's say to map the reservoir geothermal. And then the third objective is we can, let's say, give some useful information to the let's say government of Saudi Arabia or other institute. First of all, about the basic theory, I think in this I mean paper and in books is already mentioned many times. But basically, the MT is the passive method, which means you use, you know, natural resources, and then it can be represented in the two elements, the impedance tensor and tipple. Impedance tensor, this is the equation. The impedance tensor is like relation between the horizontal component of the magnetic field and then with the electric field. But the tipple is a relation between the electric field and the vertical component of the magnetic field. And then this, I mean, from the impedance tensor, we can calculate the upper necessity, and we can also calculate the phase. And then in this part, if the the resistivity is increasing, then the phase will be less than 45 degrees. But if it is the same like a homogeneous half space, the phase will be 45 degrees, and so on. I mean, and then another thing is in empty, we can calculate also the skin depth. It is the equation like 503 times square root of resistivity times period. So for example, if we have, because in the end we will have a transfer function, then we can calculate in particular frequency or period, we can calculate the skin depth. And then another thing is mentioned here is about the geothermal. It's always because geothermal is related to the liquid, related to the high temperature. It means this, of course, like conductive target and will be attractive target for EM method. And then because of some advantages, MT is like the most EM method to be applicable for geothermal exploration. Before do any field survey, we have to understand also about the data distortion. For example, in my case is empty. I try to summary about this empty data distortion. Basically, there are two main source about that can affect the empty data. First is shallow part, shallow inhomogeneous part. And then the second is the topography. So these two things can affect the empty data. And they call it, this galvanic distortion, either from near surface heterogeneous or from topography. They call it static shift effect. And then this static effect, before do any inversion, we have to remove this kind of distortion. And then I summarize also here is there are several approaches how to remove this static effect. First, we can do, for example, 1D TEM measurement. And then if we measure in the same side of the empty, then we can use this TEM as a constraint to correct the static effect. That's why in this study, I use this TEM to correct this static effect. But there is another approach. For example, the smooth regression joint inversion. This like as I understand, we have a couple of many empty recording, and then we do like mean, let's say, inversion, and then we will use the mean value of mean inversion to correct other empty data. And then the third approach is to incorporating the topography. This also something like proposed by Cumming and McKee in 2010. So if we area, it has a slope from the topography of the mountain, then the empty data will affect because of this topography. That's when if we incorporate this topography during the inversion, then the static shift will be corrected. So another thing about this empty is if we have this impedance tensor, then we can analyze about the conductivity structure with either 1D, 2D, or 3D. I just this summary because to save the time, I will just go quickly. So I mentioned also here about the TEM method is one of the induction method. Basically, it is, I will go next. So it has like a two coil. One is transmitter, the small one is the receiver. So the transmitter inject the current, inject the current to the subsurface, and then it will measure this primary field. And then start from the current flow is going down, and then when we immediately stop, and then there is like effect, coming from the subsurface, and then we will record the secondary field. again for the regarding this TEM, if we use a larger coil, we will image deeper target. And also from this the receiver, if we use a little bit also, it will also capture deeper target. Now I will talk about this the conceptual model of the geothermal system. Of course, we have to understand, after we collect the data and so on, we have to compare with like what is geothermal system look like. So at least I found like 2 different model, but basically like almost the same. So for example, there are 4 parts. First part is resistive failure, and then the second part is the conductive coil cap. It's very conductive. And then the third layer is the reservoir. It's a little bit more resistive. And then the fourth part is the heat source. It's like the common, the common geothermal system. However, some researchers suggest that for example, geothermal system related with the high temperature volcanism, the coil cap may be absent. It means sometimes the coil cap is not visible in the for the geothermal system with the high temperature. Then it's very important because my result in the end, we will see what belongs to which model and what will happen. Okay, we start data acquisition. First, this from empty instrument we use for the field is from the KMS technologies. Basically, in empty we have induction coil from the component of B, X, B, Y, and BZ. And then we have 4 electrodes to be connected east, west, and then north, south. And then we have a couple of different accessories. We use also bentonite to lower the resistivity and so on. And then this is the layout I'm using for my study. So the thing is about this value. So because we use the cable to lay down this to connect the electrode. Actually, what they suggest is if we use a larger cable, or let's say larger distance between electrode, we can increase signal to noise ratio. It means we will have better data. But unfortunately, because in our area sometimes we could not measure like 100 by 100 because it is 50, it means 100 by 100. So we have to shorter the distance. We use like sometimes 40 by 40, sometimes 50 by 50 or 60 by 60. Because it depends, this the area. And also in my field work is BZ or the vertical coil. We only install in several stations, not all stations. Because it's because of limited people and so on. It's not easy to bury like 1 meter long in the ground. If our ground is like like rocky mountain, it's not easy. That's why we install like several points. This is the instrument using for TEM. So the previous one is for MT, this is for TM. We use from IBM TM, and then with the 40 by 40 loop. It's also again, if we use larger loop, it will be deeper. It will also be, good actually. But again, because of some limitation, the people, the power, and so on, the logistic and so on, and also the site. So we decide to use 40 by 40. This is some picture from the field work. This is while we are installing the empty measurement. In the middle is we call this TM measurement. Then this I show here because the first stage we measure like couple of measurement and a 15 empty station, and then in stage 1, because we went twice, we measure 35 empty station but only 13 TM soundings. It means like we have 50 empty station, but we have only 13 TM sounding. What happened is because of this problem. It was like really, very bad weather and big flood, and we could not continue the measurement. This is the distribution of our empty station. The one with the circle is with BZ installed. So we have like actually 49 because we have 50, but one station will not use because the data is very bad. So its total is 49 station. With this sum of them, it has a vertical component. The vertical component gain is only deal with the tipple, not the impedance tensor. And then the TM sounding, this I just record from TM01, it means TM measurement in MT1. So we have here like for example, MT1, MT5, and so on. TM1, it means in MT1, TM5, 26, and so on and so on. Another thing is I want to mention here is we record MT using 3 different sampling frequency, 4 kHz, 1 kHz, and 40 Hz with the different time recording. So in general, we record this MT between 5 to 7 hours. Now we move to the data processing. So this is the what I'm doing the data processing. Basically, first we call it pre-processing, and then processing, and then F manager. And then pre-processing, the main thing is we want to make sure that the QC, the data quality control, data QC is we have like acceptable data. And also in this step, we check, the original, the raw data to be sure that we have like 5 components and then everything is connected properly. Otherwise, if there is mistake during the connection, we can revise from here. We call it channel remapping. And also in this step, we analyze also spectra and coherence. I will show you afterward. After that, after everything, we have to, we make sure that everything is set properly, and then we move to processing. This processing, we are using robust statistical method from KMS, but developed by Maxim 2003. Basically, we are dealing with FFT, and also there is coherence threshold, and then also notch filter to filter the power line. And also in this process, we have to make sure that the sensor calibration factor is correct one. And then after that, we will analyze this. We will have like transfer function, but not the final, not the final one. So then we process again. For example, we will estimate the average to get like final transfer function and so on. So here is from this paper, I try to summarize what is going on during the MT data processing. So first of all, like it's too much. So just basically like this. So the raw data in time series, we will divide into different segments, and then from this segment, they will analyze also like the coherence and so on. And then if this data, because we set the coherence threshold, if it is below this threshold, and then they will try to remove. And then there is what he mentioned is, wait, I will show you, where is the auto-regressive model. So first identify the layer and the gap, they remove, and then try to, let's say, like do replacement. And then if it is the threshold is not fulfilled, I mean, the coherence is below the threshold, and then they will also remove this segment. It means we will doing this processing, we will like take only, let's say, the good quality data. But of course, it depends our threshold. I mean, sometimes we put like 0.6 or 0.8 and so on. Another thing is, what about this power and noise? We use this notch filter because we have like 60 Hz harmonic noise or 50 Hz harmonic noise, and then we will use this notch filter to remove this large noise from a power line. And then in the end, then we will apply this the seizure to do this statistical calculation. So here is the sample of the raw data, because as I mentioned before, we record using 3 different sampling frequency. And then from each frequency, we have, sampling frequency, we have 5 channels, because we, for example, channel 1 is for BX, BY, BZ, and then EX, BY. It is also to make sure that we have like proper data, because sometimes we did not connect properly, we may lose some, one of our 2 channels. This is the example of what we are doing about the spectra and coherence analysis. So this is the spectra from MT1. So if you can see this here from the very short frequency, we have a Schumann resonance, and then this very clear, spike is noise. This spike is noise, very clear noise from the power line. This is like harmonic. For example, from 60 Hz, the second one is 120, and then the third one is 180, and so on. And we will continue like in the harmonic. And then here is the example for the coherence. This is the example for the good data. This is also the good data, the good spectra, and then it's a good coherence indication. If you can see here is the, for example, the orthogonal channel, it will have high coherence. If it is parallel component, it will have low coherence. But if you look at here, the bio, picture, there is, like not quite smooth, and also after power line noise, there is also another noise. It form MT7. The same, signal, if we analyze this coherence, also very strange. For example, here in this part, we have it should be, as I said, if it is orthogonal, it should be high coherence. But this part, you can see it's very low and like all the same. But parallel and orthogonal is the same. That's why in this data, for example, MT1, we can say like good data, but MT7 is very bad data. That's why we will not use this MT7 during the inversion. This also example, this from MT2. So in MT2, we did like 3 times measurement. What happened is, this is the first measurement, and then after we analyze everything, we do the processing, we have very strange result. You can see here it's like more than 1 million ohm meter. This is really not possible. This really, there is something problem. And then we repeat again, because after we see this, doing the data QC, and then we repeat again the second measurement. It looks, not so good, but still okay. From this data, this from the same station. This is the result from MT7, as I showed before, because it's this many noise, many strange, indication. You can see also this, the transfer function is very strange. It's like more than 1 million also. This way, then we say, okay, we cannot use this part. And then we measure not the same occasion, we move like 150 meter next to the MT7, and then we call it MT15. Then the result is very good. This, I mean, good things to, I mean, you know, always to do during this MT measurement. We cannot say just do measurement and then go back and then no, we have after finish 1 day measurement, and then we have to like analyze the, you know, data quality and so on, and until we satisfy, and then we can move to the next station. Otherwise, we have to repeat some station because of the quality. This is the final result from MT processing. This is like some of the good result from MT4, MT8, MT24, MT44. So this also from this transfer function, because transfer function is, you know, upper necessity and phase. From this transfer function, we can even see that we will have like conductive target, because it is going decreasing. Decreasing necessities mean we will have conductive target. This happened for almost, I mean, all station. It's also, I mean, can be validated using the phase. If the resistivity is decreasing, then we have more than 45 degree of phase. This always also for, I mean, more than 45. This is more than 45. Also, this part some is a little bit after conductive. We will have also, and so on. So now I will talk about the TM data. So we measure, as I mentioned before, we measure actually 13 point, but out of 13 point, the good is only 11. The good data is only 11 out of 13. But this, I mean, example of the good data I have. So basically in TM, we will have like three different data, I can say. So in the top, I mean, in the green one is the high moment, and then the blue one is low moment, and then this there are so many with the data point. This noise. So from this TM, what we do is we have to select like which one is the good one, which one is noise. Like we have to spread. For example, in this part, I still keep pick this part of the data because still like continuity from the previous data. And then afterward, we do 1D processing, 1D inversion. So this is the same data. So after we take it out the noise, and then we run the inversion, there are two options. I mean, smooth or riot model. The smooth model is about 20 layers, and then depth of investigation is 190 meter. And then in the riot model, we just 5 layers, but again it's 100. And then the good thing is, you know, the data residual is again indicate, I mean, this is a good data. And then from after we process the TM data, and then we can use for static correction, as I mentioned before, to deal with the empty data distortion. It is using this software. I mean, I do is first we upload the empty data, and then as well as the TM data. And then what we do next is to apply joint inversion, between TM and then MT, because TM is basically major shallow part, but MT is deeper part, and then we do a joint inversion, the shallow and deeper part. After we got this model, I mean, from the 1D joint inversion, and then we will have this kind of response. And then from this response, and then we can shift the empty data. So this one is before shifting, and then the right one is after shifting. You can see this like a little bit difference. For example, the blue data is started from 1000 resistivity. And then after shifting, a little bit like 700 maybe ohm meter. And then we do for all 11 empty stations, because we measure only 13, but out of 13 we only 11 is good. Now next, after we apply the static correction, and then we can do another analysis. This figure is from phase tensor. In the phase tensor, there are like two parameters, alpha and beta. Basically, like alpha, we can say like indication or indicate of the strike direction, and then the beta shown in the color is indicate dimensionality. If it is large beta, like plus minus 3 or plus minus 4 between this, indicate 3D subsurface structure. So we can see from here, for example, this short period is 1 second period in the 4, and then this long period. You can see from the short period, it's like 1D or 2D. Only few, like we can say, like not 3D. So, but most of them is either 1D or 2D. But in the long period, it means the deeper part, mostly we have 3D. So from this phase tensor analysis, we can say this model will be very good if we apply 3D inversion model. And also it's indicate, this, as I said, this strike of strike direction is also, because we have like a far away here, it's also indicate this direction. It's good, data. Interesting data. So another thing is, I process also the typo data from the vertical magnetic coil. So from also again from the short period to the long period. So in the typo, it's basically indicate the typo it has a direction. The direction is from resistive to conductive. If you see the result, so from this not really short, but let's say like in the mid period, we will have a conductive target in this area. You can see all, like almost all this typo is hitting this part, also this one. Only in the deeper, in the long period or deeper part is a little bit going to the southwest direction. And then we can use this to validate our final model. Now we move to 2D inversion. So first, the impedance tensor for the 2D is rotated based on the geoelectric strike analysis. This is like a mass. Before we do any 2D inversion, we have to rotate, because we have already the analysis from the previous result, and then we just rotate the data for all the sounding to this strike direction. And then I use this smoothness constraints to do the inversion. And then again, I use this, we call it effective impedance. So effective impedance, because in the impedance, in the Z, there's the component XY and YX, or TE and MT mode, TE and TM mode. So plus, and then divided by 2, we call it effective impedance. This is what I use during the inversion. And then I generate like full profile from out of 50 sounding empty station. So I will call it P1, P2, P3, P4. Here is the profile. P1 is the longest profile, and then P2 cross a little bit cross this. The style is the hot spring, and then this P3, P4, and then this result from the P1, the longest profile, and then you can see from here, this the green one is the conductive anomaly, and then this the red arrow is hot spring. this we can see like, okay, then the model looks good, because this hot spring exactly like almost exactly this view of this hot spring. We have a conductive anomaly. And for the another profile, this P2, P3, and P4 is also indicate like we have this conductive anomaly. We have also conductive anomaly, and all this conductive anomaly is almost exactly below this hot spring. And then we can compare with the, the geothermal conceptual model. As I mentioned before, basically in geothermal, we have resistive layers, and then conductive from the clay cap, and then we have this reservoir is about 100 ohm, and then below reservoir we have heat source. So from this model, this reservoir is exactly 80 to 100 ohm meter. Also from the other profile, also it's like 80 to 100 ohm meter. And what about the clay cap? In my presentation before, I mentioned that based on the couple of studies, if we have a high temperature, and also this, if the geothermal is related to volcanic, is exactly what I have. I mean, in my study, the clay cap mostly will not available. This is what I mean happen in this area. So we don't have the clay cap. So after this like resistive layers, and then we have the reservoir. We thought this is the clay cap, and then below the reservoir we had the heat body, like or heat source. This is the model. I mean conceptual model. So this is the data feed from different station, and now we move to 3D inversion. I'm using this multi-M software developed by Albert 2014, and then it used finite difference. The main thing is like we develop like a cell grid. In this cell, the electric field is defined along the edge. The E is along the edge, and then the edge or the magnetic field is along the shell face or the side. And then from this definition, I try to develop, to build initial model. From this initial model, this what I use. I tried also different parameters. For example, like starting resistivity, I tried different like 700 and this is 300. And then also the cell dimension is 109 times 109 meter, like 109 times the cell, the cell dimension. It also, I tried a different size of cell, but again, this one like giving like the optimum result. And then the starting depth is 25 meter, and then the number of layers 45, and then this also like a depth increment 1.2. And then in this model, I did not incorporate the topography because I did actually this another process, but the result is not quite good. I was thinking what happened might be because we already the correct static shift, because basically the topography is will produce also the static shift problem. But if we already correct this problem, then in my opinion, then no need to again to incorporate, because if I incorporate this topography, then the result looks, we can discuss. But I did not mention. I did not show here, but this is what the reason. I mean, this is the like optimum model without incorporate this topography. And then I choose also smoothing factor 0.2. And then this the black one is the empty sounding. Of course, after this, this static shift and so on. And then the data I use is full impedance from the Z, and then also the full vertical component from the tipple. So I use both of them. And then this is the result. This depth slices is from 0 to 0.5, and then here is 0.5 until like 5 kilometers. So there's a different depth slices. So from from the top, from 0, and then the model is keep changing, and then until we like a depth like 1.8 or 2, so I say, we start having conductive body. And then the final 3D model is this. So the yellow arrow is indicate the hot spring. That's hot spring. So you can see here, this is like we have conductive body, conductive target, big conductive target. It has like 60 to 125 ohm meter. And then starting, let's say, from 2.1 kilometer until more than 6.6 kilometer. And then again, if you compare to this model, I mean the conceptual model, again it's little, because they said it's like 100 ohm meter, the reservoir. If we have like 60 to 125 ohm meter, we can say like, yes, we have geothermal reservoir in this area, I mean, in this particular depth, almost exactly below the hot spring. Yeah, okay, thank you. First of all, to the professionals, Petrisikan, Sopios, Pritam, and also some other team, and also from CPG, College of Petroleum Engineering, from KFUPM in Saudi Arabia, and also Research Center for Renewable Energy, because this the people who fund this project. Okay, thank you. Sorry, yes. What do you mean by some?
You have difficulties to make installations.
Yes, in the beginning, I mean, because in the like couple of first measurement, I don't know what happened is because we have LC5, LC200. I think you have also the IBM system, no? Yeah. So actually, it's I mean better to use LC200, but we tried it's not working. I mean, I don't know. I mean, we keep recording, but when we do this inversion, they said the good data point is not sufficient, because at least it needs like 6 data point for each inversion, and this the good data point is not sufficient. It means like 4 or 5. I mean below the 6 data point. And then again we try nothing, and then we change to LC5, the small loop, and it works. I mean, the record, and then doing the inversion also.
It works means you have no oscillations.
What is no is Um, I mean, because oscillation is, it happen inside the loops. It's not easy to, let's say, to see exactly, but at least from the result, we can see it's working or not. I mean, because it's not feasible. I mean, that's what I mean. We can see after finish the recording, and then we see the data. If we have a good, I mean, enough good data, then it's we can say. uh, 20, but 40 by 40, what you call it is small, or I mean big, because we have 40 by 40, 100 by 100, and then we test together, but not in this place. But again, the 100 by 100 give much better result, because it's very clear, like the high moment, I mean high moment and then low moment, because in this 40 by 40, the low moment is, it's like reaching already the noise level. But in the 100 by 100, it's still like we have long, long curve from the high moment as well as the low moment, and then it can go like much deeper also. But the data, yes, because I have also in my computer. But yeah, this 100 by 100, I mean the larger loop will give you, I mean, much better data. Yes, again, this because we use like how long is the sense? Like 120? Yeah, 120 centi. And then this area is rocky because it's mountain, And then we have limited people, limited power. So that's why we can like install one BZ every day. Okay. If we measure like 3 stations, only one have the BZ. And then in scientific reason is because BZ is dealing with the lateral variation. It's not necessary because the spacing in my code is like 300 meters. The space, I mean the distance between station. We like do not expect. I mean, for example, like in 500 or let's say 700, we will have lateral variation. It means if we install like one BZ every 3 station, it will be, let's say, enough. I mean, actually what we're doing is we were trying to optimize the time also based on this theory. I mean, if the lateral variation is not really, you can just ignore. I mean, you see. Oh, it's always good. I mean, if you can install this BZ, because in the tipper will be very clear the conductive. Yeah.
Main reason is, I think, very terrain.
Mhm. No, this in our case we install it, yeah, like because we have 3 coil. First, for example, the BX, we install BX there, and then BY there, then BZ there. When we have to install one by one. I mean, it's not one, instrument, and we know this because it has like extension cable like 20 meter for each coil, induction coil.
Of course, apparently some of your transfer functions were affected by the shift and you corrected them, but then of course you applied some static factor on them. I'm just wondering, why you have a problem with the model including topography, check the data fit and check where actually in the forward calculated data or the model data some kind of static shift which could be created by the topography which is detected because I'm wondering, like one thing also of course one different topic what much it doesn't include a process like that kind of high transfer function because usually the topography effect because also because the electric field from the surface and stuff.
Yeah, actually, I did also, but I did not shown here the forward modeling on my study area, because in the study area we have like slope. I mean, we have far away, then there is a mountain, and then also mountain, and then I did also the forward modeling to incorporate this topography. Yes, it affect quite significant on the transfer function. If this, because very clear in the curve, because I did this homogeneous. I need to show. Oh no, okay. So like a homogeneous with topography, and then the transfer function, because in homogeneous should be straight. I mean, for example, phase is 45, and then the apparentity is like in the one number, then go straight because homogeneous have space. But using this topography, it will shift this somehow the transfer function, and then if we do inversion using this transfer function affected by topography, and then the model, the result about the inversion result is not anymore homogeneous. It means this topography gives significant effect to the transfer function. But again, if this transfer function, because it's like also shift, then I don't know. That's why this because I already corrected this static shift, and then use the without topography and with topography. See, yeah, okay, yeah.
Abdul Latif, can you hear me?
Code? Yes.
Can you hear me?
Yes, yes.
Okay. Only if you can hear me. I have some detailed question to some of the slides.
Yes.
Can you go to slide number 32?
Number 30. Wait. I think this one is the 32, yeah.
Yeah, no, 32. What do you call data residual? Is that your RMS error, or is that your chi-square? What is your data residual?
I'm not sure, but it should be LMS. But I need to check. But because in
Yeah,
the,
just check it. It's okay.
Yeah.
It's okay. Just check it because
Okay.
otherwise it's not clear.
Mm.
And number 34.
34. Okay.
So you said that you derive from here that this is good for 3D inversion. How? You have to elaborate on that. How do you see from here that this is good for 3D inversion?
Because the beta is indicated.
Can everybody hear me, or am I only talking to you?
Oh, you did not hear this. Okay.
So you have to repeat my question if they cannot hear.
Yeah, but actually,
So
because in phase tensor, it has two let's say parameters, alpha and beta. Okay, and this beta indicated by chiral code is if it is more than plus minus like 3 degree, is indicate 3D subsurface structure or 3D conductivity structure. That's why from this, for example, this period 4 and period 11 is all occupied by red color. It means somewhere here. I mean plus minus 4, let's say. And then from this value, it means this model will be 3D conductivity structure. That's why, I mean, because of 3D, then sorry.
Yeah, you may want to write this down to get that clear and describe that clearly. That's fine. You've answered my question. Okay, thanks. I've one more simple one. You after the discussion, if you go back to where you have the TEM joint inversion with the MT. Now you have some instrument problems with your TEM instrument. If you see this conductor near surface and both of the plots shifted and unshifted on the right, that the very near surface one. So that clearly is related to your instrument, to your consideration and the receiver of your transmitter. And you do have, because you mentioned it, that you have very rocky environment, so that's why you need a larger loop to average that out. Is this the 40-meter loop or is this the 100-meter loop?
This is 40 by 40.
This is 40 by 40. So do you see this conductor near surface also with 100 by 100?
I need to check because 100 by 100 is not in my study area because it's in from different.
Okay, all right. Because it's not, you don't have any groundwater table or anything like this. You don't have any near surface conductor there. So this very shallow conductive layer has something to do with your instrument.
But okay, but this one is
I'm not saying that it affects your data. You may want to leave that out, but you need to be aware that that's an instrumental issue.
Okay.
Doch, wir haben hier eine Vorlesung jetzt. Wir müssen jetzt aufhören.
Okay. That was my last question anyway.
Okay.
And sorry for the interruption. We have a lecture now.
Okay.
Okay, so thank you for the participation. And
thank you. Now because we are closing because there will be another lecture in this place. So
yeah.
Okay. Thank you.
Okay.
Also thank you for. Okay, stop recording. Okay.